Greetings, peeps! Hey, we got a stationary wave source right here. Well, what does that mean? It's an object creating waves. It's creating little ripples, perhaps in a pond or whatnot, but we can also extend this to a three-dimensional environment with the phenomena of sound. So here's what's happening. The medium is the same, the temperature is the same, so the wave velocity is going to be the same in each direction, which also means that if I'm standing over here to the right, I'm going to perceive the same frequency as somebody who's over here to the left. I'm going to hear exactly the same thing, exactly the same pitch if it were the phenomena of sound. Well, that sounds kind of trivial, but I want to show you in animation what this looks like so that when we get to more complex cases, when we set the wave source into motion, it makes more sense. All right, so here we go. Boom. We're going to create an object here. It's a jet, and it's creating waves. And those waves are going in each direction. So again, if I'm to the right, I'm perceiving the same frequency as to the left. The wavelengths are the same, and everything sounds the same with this object, no matter where you are, because indeed it is stationary. Well, let's look at another case where we have an object in motion. That's called the Doppler effect. A wave source moves to the right in this case, and the speed is less than the speed of the wave. So the object's moving slower than the wave itself. So in this case, slower than the speed of sound, or slower than the speed of the waves in water. And so it's creating a wave, but because it's moving to the right, these waves get bunched up together. And so someone who's on the right will perceive a frequency higher than the original. If someone is on to the left, the opposite happens. These waves are being stretched apart because every time a wave is created, the source moves a little bit away. Another one's created, the source moves away. And so what happens is they get stretched out. And so if you're standing over here, if the source is moving away from you, then the perceived frequency is lower than the original. All right, that's kind of weird, but let's take a look at it. Maybe in animation it makes a little more sense. All right, so here we are, and I'm going to present the plane over here. Boom. Now what I can do is drag and create an arrow, and I can create a big arrow, and really up here, this is the ratio of the velocity of the object versus the velocity of, in this case, sound. So let's go at half the speed of sound. That's Mach 0.5. I'll do that over here and set that to about 0.5 like that, and it's into motion. Okay, now look at this. Notice that over here, the waves are closer together as the source is moving in that direction. And the frequency, how often I would hear it over here versus over here, and versus the original, there's a change. We have higher frequency here compared to the original, lower frequency here compared to the original. And so that's something that is definitely perceivable in sound as a pitch change. And of course in light, actually, we can detect that as a color shift, as a color change. All right, so, well, what could we do with stuff like this? Actually, several things. And one of those things is, well, hey, we can make some calculations about what the observed frequency is if we know things like what's the velocity of the wave. Like, so what's the velocity of the wave, let's say the speed of sound. So if we know the temperature, we can find the speed of sound in air. How fast is the object moving? And what's the original frequency? We could find the observed frequency if, note the bottom over here, when we select positive, the object is moving away, and negative towards, okay? So in this case over here with the towards case, the frequency goes up. In the away case, the observed frequency goes down with respect to the original. We can also look at it in terms of the velocity of the object, okay? We can actually find the velocity of an object if we know what the velocity of the wave is, and if we know the original frequency, have a measurement of that, and the frequency of the observed. Sounds kind of weird. We'll actually do this. We'll actually do this with car horn, okay? Well, what's another case, maybe? If you go at the velocity of the wave, so in our case, let's say we can go at the speed of sound with a jet or something very, very fast, the wave source moves to the right at speed equal to the wave speed. And what happens is that here, all these layered pressure fronts develop, and so it's quite a task. It takes a bit of energy. You need a little boost to get through this barrier. That would be like breaking the sound barrier, for instance. And once you do, it's kind of smooth sailing, smooth traveling after that. Let me show you what that looks like again in animation. So we'll go over here and we'll start this up in such a way we'll be moving at Mach 1, the speed of sound. So I'll be very careful to choose the value of 1, exactly 1, like this. All right, check it out. So now we're moving at the speed of sound. Man, this pressure front just building and building and building and building and building and building and building. So you can see how all these layers mean that it's quite difficult to get through. So you should, I guess the planes should be aerodynamic. They can pierce through, but also they need an energy and a thrust to be able to do that in the case of sound like this, okay? What happens though when you actually do break the barrier? Or in the case of water waves, a bow wave is developed. So let's check that out. One last set over here is a bow wave in 2 dimensionals, or a shock wave in 3D is developed, and the wave source moves in this case to the right in speed excess of the wave speed. So we have these places here where there's constructive interference that could occur, and this high pressure on the sides is actually going to be permeated in directions up and down, and so you would hear this as a sonic boom if it's a sound wave. So over here we go back and we'll check that out. What is it like when you're moving faster than the speed of sound? Well, let's try a couple examples. Let's go Mach 1.2, a little bit faster, so like this. And notice that the jet is going basically past this front. There's still like this cone of activity here. There's still a lot of pressure, but the object is moving past it. Now, if you're going much faster than the speed of sound, let's say Mach 2 in this case, you'll really see the difference here where the object is just totally like leaving behind, it's creating those waves, but leaving behind that pressure front. So no part is over here. And so, yes, that's nice. Okay. That's what it is, folks. All right. Thank you much. Be well. We're going to do some cool Doppler stuff. Morad out. Ah, ooh, ee.